I'm not feeling well, so I'm going to be gone today, and I did not bring my iPad home with me to make a video, so we're going to have to do this like a screencast. I would suggest that you watch this and just kind of follow along. I'll try to keep it brief. Then go to the PDF and copy down the notes from the PDF. But once you have a little bit of an understanding from watching the video, hopefully the notes on the PDF will make a little bit more sense. So in this unit, Unit 7 is about exponential and logarithmic functions. This is a pair of functions that are another type of inverse relationship. So in the last unit, we talked about inverses. Specifically, we worked with radicals and exponents being inverses of each other. And so we're introducing two new parent functions in this unit. And we're going to start in section 1 by looking at exponential functions. Okay, so an exponential function takes the form of y equals a times b to the x. The parent function is just b to the x. And b can be any positive real number. So there's actually a whole lot of different kinds of parent functions because b can be any number, but it'll always take this form. It's called an exponential function because the x, the variable, is the exponent. It's different from like a quadratic where it's x squared. The exponent there is known, it's 2. But in this case, the unknown value is the exponent. Okay, so there's two different ways that this can happen. If the value of b is greater than 1, then the function is called exponential growth. And if the value of b is between 0 and 1, the function is called exponential decay. So here's what the graphs look like. There's two different ones for growth and decay. Let's just focus on growth for a minute. And the characteristics that you need to understand here. Every time I graph these, I make a table of values where I choose -1, 0, and 1 for my x's, okay? And we get this shape here where, remember, if I do a negative exponent, that doesn't make my answer negative. It flips it, so it makes it a fraction. So that's why as I move out to the left, the numbers are getting smaller and smaller and smaller and smaller. B to the -1 is 1 over b. B to the -2 is 1 over b squared. So it's getting teeny, 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 but the answer will never be 0. So it never actually gets to the x-axis. It just gets really, really close to it. And so that is a new bit of vocabulary here. The x-axis for exponential growth and decay functions is called an asymptote. Now, usually when we graph these, we draw a dotted line to represent where the asymptote goes. So here's an example of that. When I graph this here, you see I graph this dotted line. So you may want to add that into these sketches here. But an asymptote is an invisible line. So it's not actually part of like the function as far as the ordered pairs of the function, but it is part of the function because it's a boundary line that occurs. And that's why we sketch it with a dotted line, because those ordered pairs don't work in the function, but it is a boundary. It's like a fence. So we sketch it with a dotted line. The graph gets closer and closer and closer to an asymptote, but it never actually touches it. So since there's an arrow on the left and an arrow on the right, the domain is all real numbers, but the range is only above the y-axis or the x-axis, and it never touches the x-axis. So it's y greater than 0, not greater than or equal to 0. Or you could say 0 to infinity with parentheses on both sides if you wanted to, if you're using interval notation. So exponential growth increases from left to right. Exponential decay decreases from left to right. So it starts with a very high value and goes down, okay? But other than that, it's the same. Again, the way you tell the difference between growth and decay is the value of b. B is between 0 and 1, it's decay. If b is greater, it is growth. Okay, so this is where you may just want to listen for a minute, and then you can go back and copy this down from the PDF, because I'm not, or pause the video as you're watching, but I'm going to talk through this, and I'm not going to leave a lot of time for you to copy down. So if I look at number 1, it says tell whether the function represents exponential growth or decay, then make a table of values to graph the function, including the asymptote. The asymptote is always horizontal for these functions. So this is the parent function where b is equal to 2. Since 2 is bigger than 1, this is exponential growth. I always make the same table, -1, 0, and 1 for my x's. So we just plug in 2 to the negative 1 becomes 1 over 2. Remember that negative exponents flip whatever the base is, okay? If I plug in 0, 2 to the 0, anything to the 0 power is 1. And then 2 to the first is 2. So those are my 3 points. So I sketch those 3 points. Dink, dink, dink. And it's always going to make this kind of elbow curve. So you sketch your asymptote. Here it's at y equals 0 with a dotted line. And then it should increase from left to right because it's growth. So you're just going to kind of skim along and then follow the dots. Oops. Follow the dots. And that is your graph of this function. So here's one that is decay. Here the base is 1/2. And so again, negative exponents flip. So 1 over 2 to the negative 1 power is going to become 2 over 1. So it's 2. And then we get the other y values. So this one is the same. We're going to plot the points, but this one is going to decrease from left to right. And as you move to the right, it just skims that asymptote. Okay? An asymptote must be a dotted line. That's the only correct way to draw it. So I'm going to leave you to copy down number 3 and 4. You can either pause it and copy it down now or copy it off of the PDF. So of course we're going to add transformations into this, okay? So just like with anything else, horizontal happens on the inside, vertical happens on the outside. Inside of an exponential function means it's happening up in the exponent. So that's where your minus h is going to come. A multiplier in front is a vertical stretch or shrink, and a plus k that's not part of the exponent is a shift up or down. So here's a couple of examples so you can see where the pieces are. Either pause and copy that down or wait and copy it off the PDF. But again, the base is just the parent function. So the base can always be different. The fact that b is equal to 3 only tells us whether it's growth or decay. It's not a transformation. It's just a different type of parent function. So anyways, you can look at those. So here's how that's going to affect the graph when you're graphing with transformations. I graph them very much the same. So we're going to start with the parent function. Most of the information will stay the same, but domain will remain negative infinity to positive infinity, but the range is restricted by the asymptote. It's y equals 0 unless you move the function up or down. That will change. So it'll change the range as well, and we'll see that in this first example, okay? So I have y equals 3 to the x minus 1 minus 4. That means we're going to go right 1 because the minus 1 is in the exponent, down 4. That's afterwards. The parent function is with no transformation, so that's just y equals 3 to the x. And I make my same table with negative 1, 0, and 1, as I always do. That's what these 3 dots are here, is my parent function. And then I just shift them right 1, down 4. I think it is helpful to always draw the asymptote first. So since I went down 4, the dotted line is now through y equals negative 4. And that kind of helps you know where you need to stop drawing. So I like to do that first. But each of these points is just right 1, down 4. And that's how I got the new points there. So the asymptote now is the equation y equals negative 4. Remember, we've talked about before, no bald numbers. This is a horizontal line through y equals negative 4. You have to have the y equals. Otherwise, it's just a number. It's not an equation of a line. So don't forget that. The domain is always going to be the same, negative infinity to positive infinity, or you could say all real numbers. But the range here now is going to start at 4 and go to infinity. But 4 is not included because it can't touch the asymptote. It's going to get right up next to it, but it'll never touch it. So that's why we want either parentheses on the 4, or you can say y greater than negative 4. Oh, and that should be a negative 4 on there, not a positive 4. Excuse me. Okay, let's look at one that has a vertical stretch, because I like to do the stretch as part of my table rather than doing it on the graph. So the parent function is going to be y equals 1/2 to the x. We've done that one on the previous page, so here's the y coordinates that I get. But since this one has the 2 in front, and I would do this if it had a reflection as well, you can see on number 9, anything that's a vertical multiplier, since a vertical stretch multiplies the y's by 2, I just did that off to the side before I plotted the points. So these little x's that I drew here have already been stretched by 2. and then I just moved them each to the left 4, and that's how I got this curve. Since it didn't move up or down, the asymptote is not going to change. If you take a horizontal line and slide it back and forth to the left and right, it's still the same horizontal line because it goes on forever. So the domain and range are the same as the parent function, and the asymptote is y equals 0. And then I'm going to leave 9 and 10 for you to look at yourself. But again, here on number 9, this is how I handled the reflection, was just to multiply my y's by -1 before I sketched them on here, okay? And this one should be upside down because it's a reflection. Since it went up 3, the asymptote moved up 3. So you're not going to be graphing these by hand tonight. It's just a delta math practice. Before you start the delta math, please open up the file on Canvas and copy down all of the notes so that you can kind of get practice with sketching these. It won't take you very long, but that will be all for today, and we'll review this when I get back, hopefully tomorrow, fingers crossed. I will see you guys maybe then.